My name is Gunjit Jain and I am pursuing Masters in Data Analytics. Today I am going to present my research presentation on sleep apnea detection using deep learning methodologies. So the sections to be covered in this presentations will be introduction, motivation, and then research area, research question, literature review, dataset overview, the process flow, data preparation, models to be used, implementation, evaluation metrics, conclusion, future work, acknowledgement. So, moving on to the introduction to the topic, sleep is a very important phenomena in a human's day-to-day life. Its quality has a significant impact on the health of the person. So, there are a few kind of sleep apnea called obstructive sleep apnea, which happens due to the blockage in the throat muscles, and the person stops breathing for 10 seconds to up to a minute. So, there are two kinds of sleep apnea. One is obstructive sleep apnea, another is central sleep apnea, in which the brain fails to send the signal to the respiratory muscles to breathe. So for the detection of sleep apnea, the gold standard process is polysomnography, in which a person has to visit the sleep clinic and where he has to sleep overnight, and the sleep experts monitor him throughout the night to detect sleep apnea. So most of the sleep apnea cases remain undetected as person suffering does not realize the problem himself. And even after he realizes, he doesn't go to sleep clinic to sleep whole night. So the motivation of this topic comes from the fact that the person needs to sleep whole night at the sleep clinic, and many devices will be attached to his body. So the study has shown that 200 million sleep apnea sufferers worldwide currently exist. So the motivation of this research is to detect sleep apnea at home using deep learning technologies, and at home using smartwatches, and to reduce the dependency on polysomnography. So the research area for this project is to aim to detect sleep apnea using ECG and SpO2 signal, which can be recorded in smartwatches these days. So since the project involves the task of classification through signal data, the research area for this project is data mining. So the research question that this research wants to answer is how effectively can heart rate and SpO2 data be used to predict sleep apnea through smartwatch. The literature review and the related work on this field have been divided into 5 sections: detection through heart rate variability and ECG signals, detection through respiration signals and SpO2 readings, detection using ECG and SpO2 data, detection through smartwatch data, detection through other physiological signals, and traditional methods. So in the first one, Quantum et al. Uses discrete wavelet transformation instead of Fourier transformation to analyze ECG signal. So discrete wavelet transformation is efficient in for transient signals, and ECG is a continuous signal. So in Fang et al. Introduced unsupervised feature learning for single-lead ECG because in medical related data, the feature sets are incomplete and rarely labeled properly. So unsupervised feature learning does the job without proper domain knowledge itself. The next is detection through respiration signal and SpO2 readings. Mostafa et al. Defined a deep belief network for feature extraction without domain-specific knowledge. So a deep belief network was created with 2 layers of restricted Boltzmann machine autoencoder and 1 layer of softmax type. Unsupervised learning using deep learning was used to detect feature automatically from the raw data using the deep belief network. Detection using both ECG and SpO2 data. So Gandharian has used a combination of ECG and SpO2 data to detect sleep apnea. So they have used a mutual information analysis for choosing SpO2 and ECG features. So because the implementation of deep learning techniques on the raw data takes a lot of processing ability and good data storage quality, this study uses mathematical transform and relations before training the classifier. So the next is detection through smartwatch data. So Chen et al. Has tried to detect different types of sleep apnea using commercial smartwatch. So the accelerometer of the smartwatch was used to record the signal, and the motions were captured to detect whether the person has sleep apnea or not. So another Walsh et al. Has recorded heart rate and acceleration data from the Apple smartwatch along with the PSG data, and both the data were used to detect sleep apnea. So they have also used Monte Carlo cross validation and leave out cross validation to validate the results. So Romero et al. Proposed a novel method to screen OSA using acoustic screening with deep learning. So in this research, SpO2 based detection was done. And another research was on detection through physiological signals and through traditional methods. So the use of CNN to automatically learn and extract features from the raw data is shown by Sen et al. So this study also uses a leave one out cross validation. Another study is real-time sleep apnea detection, and they have designed a smart pillow which detects the sleep apnea, and it changes its shape according to the sleep apnea periods to treat the sleep apnea. So from all this research, it is clear that SpO2 and ECG data are very important factors to detect sleep apnea. So next is the dataset overview. So we are using in this research Physionet apnea ECG data. So this data set contains the ECG and SpO2 readings of 70 people, and 8 of them has the SpO2 readings. 8% has SpO2 readings, and the readings are 7 to 10 hours long. Moving on to the process flow, first the data is collected from Physionet website, and then extraction of ECG and SpO2 signal is done from APN and dot files, and then data processing is done. In that signal downsampling was done. Moving on to signal transformation, where a signal is divided into 1-minute segments and converted into spectrograms, and then the spectrogram were converted into IGen values, and the image augmentation was done for one of the models, and then deep learning model were applied on the data, and then model evaluation and comparison, and then documentation. Moving on to data preparation. So first the signal is divided into 1-minute segments because each 1-minute segment is annotated whether it is apnea or non-apnea in the data set. Then the signals are converted into spectrograms using fast Fourier transformation, and then the spectrogram were converted into IGen values for the principal component analysis so that it can be converted into metrics. So the models to be used in this research are baseline CNN, which is designed for this purpose, and DenseNet 121 plus CNN, that is a hybrid model. So the implementation part, the baseline CNN has the first convolution 2D input layer and 3 layers of convolution 2D batch normalization and max pooling, and then one each layer of global average pooling and dense output layer having one output, so binary output. So and the another model which is created is DenseNet 121 plus CNN. So in this model, the first layer is the input layer, and then two different convolution layers are used, which is then concatenated in the third layer, and then the last layer is the dense layer for output. So the evaluation metrics for this one is accuracy. So accuracy refers to the ability of the classification model to classify the data of each category accurately. So when it comes to predicting whether diseases are present or not, accuracy has very high importance, as classifying an ill person wrongly can be dangerous in this domain. So the results of the models baseline CNN, we have got 73% accuracy in baseline CNN, but with the data after the data augmentation, the accuracy got decreased because the data augmentation adds some noise to the data in the signal data particularly. So the another model DenseNet 121 plus CNN, this model has given good accuracy in the first attempt, but after fine tuning the model, applying freezing and unfreezing layers, layers, training a few layers apart from the pre-trained layers. So this model gave exceptional outputs. So the comparison of the both these are the comparison of both the models. So the first model gave us accuracy, baseline CNN gave us accuracy of 73%, and the another model which is a fine-tuned model, DenseNet plus CNN, gave us the accuracy of 82%. So, in the conclusion, I would like to say that this research emphasizes the need of integrating deep learning methods with the domain of sleep disorder detection, and outlines the possibilities to detect sleep apnea at home using smartwatches, because it's very hard for a person to go to the sleep clinic. For this research, two specific deep learning algorithms we have designed: baseline CNN and DenseNet 1-to-1 plus CNN, that is a hybrid one. So this has been employed for detecting sleep apnea by analyzing the ECG and SpO2 signals. So in future, these models can be used to develop application for smartwatches and smartphones to detect sleep apnea at home, and other complex models like capsule networks can be applied to get better accuracy. And the SpO2 data was lesser in this data set, so another data set having sufficient SpO2 data along with ECG data can be used for this in the future. So I would like to extend my heartful thanks to Mr. Vladimir, because he has guided us, supported us, and throughout the course of this work. And I am very grateful to my parents and friends and colleagues who have helped me a lot in this project. And these are the references which I have used. And thank you so much. This is the code walkthrough of the model which has been prepared. So first we have loaded all the libraries required, like TensorFlow, Keras, SkyPy, sklearn, and then we have fetched the data from the data folder where all the signals are there for 70 persons, and annotations are saved in an APN file, whether each minute has been annotated, whether apnea or normal. So the data has been divided into train test into 80% and 20% 20% ratio, and the signals were divided into 1 minute segment, and then it has been converted into a spectrogram. So the spectrogram sample is this, and then these spectrograms have been saved into a folder. So here the train test split is there, and this spectrogram has been saved into folder test and train specific folders. So here we are saving the so this is the code walkthrough. First of all, we have loaded all the files. So this is the code walkthrough. Here we have loaded all the required libraries like TensorFlow, Keras, sklearn, SkyPy, and then we have this is the code walkthrough, and first of all, we have loaded all the library files, TensorFlow, Keras, sklearn, SkyPy, and then we have fetched the signal files from the database, and those files are for 70 persons, and each minute has been annotated whether apnea or non-apnea. So so single 1 minute section of the signals has been splitted, and then it has been converted into spectrogram. So each spectrogram has been saved into a folder, and then all the data has been divided into train and test in the ratio 8:2, and all the spectrogram has been saved into a folder of test and train to be used for models. So here we are saving the spectrograms data. So this is the data preparation part. Moving on to the second part, where we have applied the models. So first of all, we have loaded necessary libraries, and then we have done data exploration. How many images of apnea we have and non-apnea, and then we have visualized the data. So this is the spectrogram for apnea and non-apnea. And then these spectrograms have been converted into IGN values, IGN images for principal component analysis, so that these IGN images can be converted into metrics for fast processing. And then this is the average of apnea IGN values of all the IGN values for apnea and non-apnea. So the difference in both of them has been shown with the contrasting image here. And we have then created the data generators to be used for the models. And then the train generator and validation generator has been made. So now we start with creating the convolution neural network baseline. So this convolution neural network has a 4 convolution layer with max pooling layer. And this is the summary of the convolution network which has been created. And the design of the baseline convolution network is like this, and the output which this has given, the validation accuracy, the test accuracy, so the training accuracy is somewhere around 73%, and the validation accuracy is somewhere around 74%. So these are the graphs. So this graph has a little overfitting because of the lesser amount of data which has been used for the processing, and to avoid this, we try to use data augmentation. But with the data augmentation on the same model, the accuracy has decreased to like validation accuracy was 65%, and training accuracy was around 69%. So this is because the augmentation has added some noise to the data. That is why it has degraded. So we will be considering the first model, which is the better one. So these are the graphs with the augmented data on the baseline CNN model. So now we are training the same model for some more epochs to check the accuracy, but the previous one was better. And the next model is DenseNet 1-to-1 plus CNN, where CNN architecture was built on top of DenseNet 1-to-1. So this is the plot of the CNN model, where 2 convolutional network has been used with different filter sizes, and then both the network has been concatenated, and the final dense layer which takes the concatenated output. Then feature extraction has been done using the deep learning model, and these are the data generator parts, and then this has been fed to the model. So this model gives a good accuracy of 84.44%. That is the training accuracy, and the validation accuracy of around 77%. So then this model has been trained, fine-tuned, and tested again. So in the fine tuning, the layers has been freezed and unfreezed to make the trainable. So from the previous model without fine tuning, this was the graph. So this comes pretty good, and in the fine tuning, the freezing of the layer and unfreezing of the layer has been done. So last 9 layers has been made trainable. So after the fine tuning, the accuracy has increased a lot. So it is coming, the training accuracy is coming around 97%, and validation accuracy around 80%. So the fine-tuned model has been taken in consideration at the last. So in the evaluation, so for the baseline model, the accuracy, overall accuracy is coming around 73% with a good F1 score of 75, and precision and recall values are also coming near 77 and 74. So this is the confusion matrix for the baseline CNN model. So the apnea true positives of apnea are 70%, and true positive for non-apnea is around 74%. For the next these are the spectrograms for some of the spectrograms which has been detected wrongly by the model. So it has to be the true level has to be 1 apnea, but the CNN predicted is as non-apnea. So pre-trained fine-tuned model evaluation, in this the accuracy is coming around 82%, and the F1 score and recall precision are coming around 90 and 79%. So the confusion metrics, apnea true positives for the apnea are 73%, and 89% for the true positive for non-apnea. So this model has given a good accuracy, and these are some of the spectrogram which has been detected wrongly by the model. So it should be non-apnea, but the model has predicted is as apnea. So these are the comparison between the two models. The baseline model has given us accuracy of around 73%, and the fine-tuned DenseNet plus CNN model has given the accuracy of around 82%. So this was a code walkthrough. Thank you very much.